which is about 100 meters underground. It's a 26.7 kilometer particle accelerator. Just kind of straddles the border of France and Switzerland. And what do we do there? Well, we accelerate particles in two directions, and then we smash them together. And I can make a video by going back and forth with the two slides here. Right. And something interesting that I just learned the other day from one of my friends that's designing some of the ASICs that are like right at the collision point is that this thing that they call a single event upset happens at 1 hertz. I think that's interesting. A single event upset is a particle physicist's word for a bit flip. Okay, so they have to design chips that can tolerate this kind of radiation, which is flipping the bits all over the place. I guess it just ends up if they don't correct for them, it ends up in the statistical error for the measurement of the Higgs boson mass or something like that. But anyway, I thought this was quite interesting. But coming to the storage side, thankfully we don't put our disks there at the collision point. We put them several kilometers away, where we don't see many pit flips. And we stream data from these 4 detectors, CMS, ALICE, ATLAS, and LHCb, at around 10 gigabytes per second, taking about 50 petabytes per year. In addition to that, we have huge compute, like analysis batch farms working on the data, but we also have a typical IT infrastructure, which is pretty modern. We like to use all of the cool new toys, one of them being Ceph. So this tech talk is about Ceph for our IT infrastructure, not Ceph for our 50 petabytes per year. We'd love to use it for that, but not yet. But this is about the IT infrastructure. Okay? So I'll present our different Ceph clusters, some recent experience with file system, S3, and block storage use cases, and some of our initial sort of feedback trying the new features in Luminous. So here's our clusters. We started actually like 5 years ago in Ceph because of this killer app where you could do Ceph block storage with OpenStack. There still is, it's still the best, I think. So we have 2 clusters using for that in production. The largest is 5.5 petabytes, and then in our second data center, which is in Budapest, we have almost half of a petabyte there. And those clusters are around half used, and they're still running Joule. These are our most precious clusters, so we upgraded them the last after we fully trust all of the stability of the Ceph code. We're getting really into CephFS now, as managed by OpenStack Vanilla, and we're really interested in this for high-performance computing use cases that I'll describe a bit later. We have, between our test cluster and our now production cluster, we have about a petabyte of CephFS, maybe a bit over, a bit more, because we've just added a 3rd cluster, which is a hyperconverged cluster. Okay. Now, we do a little bit of physics use cases, so this is what this says here, Castor and XRD. So Castor is CERN's archive system, and XRD is a storage sort of framework that we use to build an application on top of Libredos. And there we have a 4 petabyte cluster, and we use that one as a buffer to buffer the writes before they go onto tapes. Okay? And then we have around a 1 petabyte S3 cluster that we're just sort of moving into production. I wanted to get this slide out of the way just to say that yes, we also do some, from time to time, we have as disks come through the pipeline, they arrive for our huge data use cases. We get to use them for Ceph for maybe 1 or 2 months. And we did a couple of, over the past years, we've done these tests. So we did 2 30 petabyte tests, one with Hammer and then with Joule. And then just before the release of Luminous, we did a 10,000 OSD test. And this was calculating 65 petabytes. So this actually just pointed out a couple of minor remaining scalability issues in the MGR, but I think that those were solved. So now Luminous, you can probably run 10,000 OSD cluster. I'd be more comfortable with a 5,000 OSD cluster. Okay, into CephFS. So, in previous events, I presented this, I'm doing this talk backwards, file system, then backwards to the block storage. I don't know why. But, in previous things, we talked about how we used to have, for IT infrastructure, appliances, NFS appliances, and then we replaced those with virtual NFS filers, okay? And they're working really well for us. So the basic, we have about 60 terabytes of them, around 30 of them, but the basic stack is just like Linux kernel NFS server, ZFS, using ZREP, which is a kind of nice script for doing the replication across to a different server. And these are just OpenStack VMs mounting Cinder, Ceph. And this works really well. We get, actually really, you can tune the performance to be really high. Our config management at CERN is with Puppet, and the Puppet masters access one of these virtual NFS files at like up to 50 kilohertz stacking files in this thing. So it's quite good for just one VM. But it's not scalable in several ways. So it's a pain to manage the quota for these things. When people fill up their filers, we have to like turn it off, detach it, expand the volume, play with ZFS to extend the file system. Then it's kind of boring work. It's also labor intensive. If somebody wants a new filer, you have to there's, of course anything can be scripted, but you have to add one for every user. And also, if one user needs more performance, not just more space, you have to just give them several appliances. You can't make one more performant. So, CephFS plus Vanilla has most of what we need. It's multi-tenant, so you can have many different users, and then separate them in quite a secure way, and also giving quotas to the different tenants. And then with the vanilla, with the OpenStack vanilla front end, the users get like a self-service interface to provision shares. So you give them a quota for creating like say 10 shares, and then they just click them and they get them out straight automatically. And it should be scalable performance, right? CephFS should be scalable. You should be able to add more OSDs as you need more bandwidth or space. And if you need more metadata performance, you should be able to just add more MDSs. We've been testing this in sort of pre-production with around 20 users since the middle of last year. And of course, a single MDS was a bottleneck. This one machine that we had was, someone mentioned earlier, I think it was Danny mentioned the single threadedness of the MDS. This is true. That's ready to roll out. So then with Luminous, Multi-MDS is in production, and we've now actually upgraded all of our CephFS clusters to Luminous, and we've enabled Multi-MDS, and things are working well. Now, one user has already, this is like, people are kind of dying for this, and one user has already asked for 2,000 shares quota on this, so they want to really use it. We're also using this as a scratch storage for some Kubernetes clusters that we have, so that's just to plug that it works as well. And we're also now contributing to CSIs, that's a container storage interface. It's a standard for all the different container frameworks to work together. So CephFS needs a plugin there, and we have some students working on that. Here's a couple of pictures showing multi-MDS in production. So I said that we've had these two active MDSs since we upgraded. The picture, I don't know if most works yet, but this here shows, like, on the left, this is all really brand new. So like on the 24th of January, we're still using one MDS. And this shows when you turn on two active MDSs, you can see, so the plot is like the MDS handling client requests. So that's normally the benchmark that you look at in MDS to see how busy it is. And you can see that there's like, there's some kind of spike. I think that the accounting of client requests is different from Joule to Luminous. But you can basically see that they spread the load evenly across each other. So Ceph has a built-in balancer to just balance the metadata to the servers. And we didn't do any tuning there, or very little, okay? We added a business option called MDS balance intervals equals 60. So this is how often the Ceph looks at the different directories and decides to move them around. Okay, so we just made that a little bit slower than the default. But yeah, it was just nice to see it rebalancing things with kind of like magic. The bottom plot shows when we went from 2 active to 3 active. Actually, you just see a third line come in here, and then these are stacked plots, so they relatively even out. So things seem to be working. I put all of our configuration options there. If anybody else wants to ask about those, then we can, but I don't need to go into detail here. Now, this does still, nothing, it's not perfect. This does still leave some things on our wish list. The block storage use case that Ceph is so successful with is, in my opinion, it's successful because it works really well, and it's good. But also because you can, if you have a huge enterprise environment, you can do these like throttles, you can do this quality of service throttles on the clients. So you can really trust that no one's going to start a VM, attach a volume, and then denial service your cluster. This is impossible because of these QoS limits. Now, CephFS doesn't currently have these protections, so I don't trust today that one user is not going to DOS the whole cluster. Of course, there are different techniques like pinning their share to a particular MDS or things like this. And yet the distributed QoS is coming, but I wonder if all that's a little bit too complex, and maybe we just need a very simple rate limiter on the client side. Okay, this is feedback also for the developer side. Yeah, and maybe like, okay, we'll go to the next one. Now, something about HPC on CephFS. So CERN's mostly a high throughput computing lab, so we have embarrassingly parallel workloads. That means that for the basic particle physics workloads, there's no message passing between the jobs. They just open a file, process it, produce a smaller file, and then write that to data to new storage. So actually, these kind of workloads are tolerant if storage is not like perfectly POSIX or perfectly consistent. So this is why we can build different storage systems. But there are several HPC corners in our lab. People doing like simulations of the beams or accelerator physics or quantum chromodynamics, okay? I don't know anything about that subject, but it's there. Just tell me what QCD stands for. And also ASIC design is kind of in this category. And they really do require, normally normally HPC you would run Ster or CephFS or something like that. And they require full POSIX, full consistency, parallel I/O, things like that. Here's one of these use cases, this is like another one of these interesting facts. So this is one of my friends that's doing the computing for the ASIC design for the CMS experiment. He showed us this slide. So these are one kind of, I don't know what that's called, like slice of the detector. There's these different chips that all have to be designed custom for CERN. And there's like millions of these chips, okay? Now, when they design the chips, when engineers have designed them for the different processor fab sizes, there's these so-called design rule checks. So they want to make sure that there's no like right angles or something like this. It's not my field, so I don't know. Now, with what's currently in the detector, that's like 130 nanometer. There's 17,000 rules that need to be checked. As that scales down, as the feature size scales down, the number of rule checks increases. I don't know if that's exponentially, but it increases a lot. So they need, just to be able to check their designs before sending them to the fab, they need like 12 to 60 times more CPU power. And you can't do that all in one box. So they basically need to scale to they need to scale out. This is one example of where they need to scale out. Okay. Now, CERN's approach to doing HPC is not to buy prefabricated supercomputers, okay? We like to build HPC. We like to do all of our computing with commodity parts, the cheapest thing possible. So that's like software-defined HPC instead of expensive integrated systems. On the compute side, we use something called HT Condor and something called Ster. And for us, the typical HPC storage is not very attractive, mostly because we don't have any expertise in it, so that would be like yet another storage system to operate, but also because they tend to be, I think they tend to be more expensive. I'm not too sure about that. So we have deployed CephFS, our OpenStack CephFS capabilities. We've been using that since middle of 2 years ago with like old ceph-fs. Actually, I think it was last year, not 2016. And yeah, it seems to work, and the users don't complain about performance. Okay, so there's no we haven't seen any bugs, we haven't seen crashes, we haven't seen data corruption, except once I think, where a user said that I read this file back and it had zeros instead of what I expected, and then it was some complicated thing where we had the wrong caching mode enabled on their client or something like this. But in general, it's working. So now what we want to do is merge like that NFS filer use case that we have and our HPC user use case that we have, and just turn it into the same service, the CephFS service, so that HPC is just another user of our filer service. But we like to also look at performance. So I was intrigued by a few months ago, someone posted on the CephNet list this IO 500 benchmark that they are trying to promote. Okay, this is a guy named John Bent. I don't know him. Hi, John, if you're watching. And this is, so in HPC land, there's the top 500 where we can all see what are the most, the best, biggest supercomputers in the world. So they're trying to do the same for storage now. But it is just starting out, and they want to get results for hero runs and anti-hero runs, and then share the tuning. So we've just started in the last, say, 2 weeks to have a look to see if this is working. Now, just for a bit of background, in the HPC community, there's two benchmarks that matter. There's IOR, which is like a throughput test, and there's MD test, which is a metadata test. This IO 500 also has a find. Okay, just type find and list all files. And in this test, they have like easy mode and hard mode. Easy mode is where, so you run these jobs in parallel on your cluster, and then easy mode is where every job gets its own file to do IO with, and hard mode is where they all have to write to the same file. It's a lot more hard. So, yeah, here's our initial results. This is with a Luminous cluster. This is with a hyperconverged Luminous cluster. So we have around 400 OSDs. These are running on servers where we have 4 SSDs per server, and 2 SSDs are going to like the compute side of things, and 2 SSDs are going to Ceph. And this is like, we just installed Ceph, we just prepared the OSDs, we did no tuning, we forgot, we need MDSs, so we just started some VMs in our cloud to run MDSs. Okay, so this is not like a well-designed Ceph cluster. This is just, let's just install it and see what happens. And first of all, it worked. So you can run these benchmarks. And for someone that's been using Ceph for a while, that's already like a big success. And second of all, we actually, when we compared our results, we're in the top 10. The bad news is that there are only 9 others. Okay, so it's okay. I mean, these are massive supercomputers that have been designed by teams of engineers to get the maximum storage throughput possible. So if we compare ourselves to the one that's at the bottom, we're not that far off. We're half as good as them with our just toy cluster that we just deployed one day. I think that throughput-wise things are pretty okay, but the metadata side we're lagging quite a bit behind. So this is like our score was like 1.4 gigabytes per second. We're even better than one of the clusters. Okay, but in this is IOPS. This is referring to the metadata side. So we're quite a bit behind the next cluster in metadata. So I don't know. This was fun. This is fun to do. But actually, we would like to work actually with the developers to make this better. I think this is something that where Ceph could make a big impact. Okay, Rowski way. So we do now run S3 at CERN. we hadn't for a while. We have our own object stores, so we didn't really need it. But now there's so many, we're finding that there's so many like open source software that you download and people want to build services out of this, and they just come with an S3 storage backend. So at some point it becomes embarrassing if you don't offer an S3 service inside. So now we're using, thankfully Ceph offers us so we just use it. So we basically run a pretty typical Ceph cluster, and then we have 10 VMs acting as gateways, and we start these or stop these as needed, and they all just live in a CNAME. This is an erasure coded pool, 4+2 erasure coding, min size 5 for safety. A couple of things that we tried. So Ceph lets you do something called indexless buckets. So this way you can have like you can have buckets with billions of objects, and there's no index object that becomes a bottleneck. But actually, none of our users wanted this, so we just removed the configuration from our cluster. We don't expose Rados Gateway directly to our users. We have our users actually connect to haproxy, and then haproxy forwards those requests to Rados Gateway. And this we found to be super useful. A, because we can restart Rados Gateways without the service going down. And also, we can redirect traffic for special buckets to specific Rados Gateways. So in case we have some users that are like really heavily writing to some buckets, we can just direct them to a pool of dedicated Rados Gateways. Now, a few small issues that we've seen. Since upgrading to Luminous, it seems that there's something, the memory usage is much higher. There's this option called the number of Rados handles, so this is the number of connections to the client. We had to reduce this from 8 to 1, otherwise we were just going out of memory. We're trying to integrate this with our authentication system at CERN, which is LDAP, Active Directory. We also have OpenStack, so we're trying all of these things, but we're not really succeeding. So somebody who succeeded at this, please grab me at lunch. And also, in Luminous, there's this thing called resharding, automatic resharding. So as the number of objects goes up, then it will just like split the bucket index into 2 and then forward more pieces. It looks pretty scary, and there's often messages on the mailing list about things going wrong with this. So we have disabled it for now, even though upstream seems to have it enabled by default. We have one idea. One of the members of our team has an idea for a better haproxy Rados gateway integration. So now in this ceph-mgr, there's a service map. So every time a Rados gateway starts up, it registers itself, says, "Hi, I'm here. This is my URL, and I'm ready to serve you." The way that we roll this out today is a bit slow. So we basically, like I said, we use Puppet. We do it in the VM. Puppet configures that machine, and then it exports a resource to the cluster saying that now via Puppet this thing exists. So then all the other haproxies discover via that one type of configuration when they restart, and then now they'll start using that Rados gateway. But this process takes a couple of hours actually, so it's not very dynamic. Now the idea is to use a service map, the Ceph service map to trigger this. So basically you would spawn a new Rados gateway which would register itself in the Ceph service map, and then that would, for example, have a plugin that registers the service in console, for example, and then that's maintaining some like DNS thing, which haproxy happens to know how to do. It can query like DNS SRE records to discover these Rados gateways, and then basically this would be a shortcut to get these things into production in just seconds. So if this looks like it could work, then maybe we should try it. Now onto RPT. So this is our current status, well, as of a few days ago, using OpenStack Cinder volumes with Ceph. So we have something, well, close to 4,000 images. These are like the system images or snapshots of running systems. And we have 5,100 volumes. These are attached volumes that users are storing their databases or data files or whatever they need for their applications. The plot is going from the left, it's from the beginning of 2016 up until now. So you can see like an increase in the number of IOPS in the cluster with some glitch at some point. And the increase is generally increasing, right? Where I start to sweat is that I look at the write latency very closely. So at the beginning, our goal is, in our block storage service, is to maintain write performance, which is like equivalent to a local attached disk. So like 100 IOPS, basically, which means that you need to have the write latency below around 10 milliseconds. And that's how it was at the beginning. But then over time, it slowly crept up as users were using it. Then we changed the hardware completely. We upgraded the hardware, which brought it back down. We did that a couple of times, added capacity. But now we're at this point where the latency is creeping up, and we need to find a new solution to add IOPS capacity. So yeah, just to wrap up, just to say that these use cases are working reliable. There's very little user complaints. We don't have a big support team running Ceph for block storage. It's quite reliable. We did also just have the pleasure of being able to update all of our clients to Luminous version 12.2.2. This was really exciting. I don't know if someone else experienced this, but thanks to a very famous security exploit released earlier this year, we got to read all of our hypervisors, which was a pain for the hypervisor guys, but for me it was great because now I don't have old legacy Ceph clients attached to the cluster anymore. So we have some, we do a little bit of development here and there. Some things that we just finished is RBD trash feature. So now when you delete an image, it won't actually delete it, it will just move it to a trash bin. Now about that increasing latency, one of our top wishlist items has always been write back cache in the hypervisor so that instead of going off the Ceph cluster every time the user flushes or does an fsync, it will just write to a local SSD because we usually have like a couple of hundred spare gigabytes that could be used for that. And actually Rackspace has now funded a CERN fellow, that's like a CERN engineer, to work on this project. So we are now just starting this up like this week. Really excited about that. And we're also now, we're on the OpenStack side, one of my colleagues is writing a backup driver for our clients. So that we'll be able to back up the images back our spot. Here's some news about when we updated from Joule to Luminous. So for the clusters that we did upgrade, things were quite uneventful. I did notice that, I think that anyone that's running CentOS probably noticed that it's not usual, but this time, like the daemons restart when you upgrade the RPM, and actually it's doing it too early. I think there's some kind of bug there, so watch out for that if you are updating your clusters. Sometimes you have to restart the daemon again, because it RPM said restart the daemon, but actually the binary hadn't been replaced with the Luminous version yet. In previous talks, I've presented a lot of the work that we do to balance data in the clusters, to replace hardware or to bring in new hardware. And we have scripts so that storage step/subscript does a GitHub thing where we keep those scripts. But in Luminous, there's something now called the balancer module. And this thing is so it's like a built-in feature to hopefully do what several Ceph users have had to do manually with scripts. This thing has two modes as of now. One is called crush compat, so crush compatible mode, and one is called upmap. Now just very quickly what those do, so I did a little bit of, I was reading to see how they work. So the crush compat mode is interesting when you have old clients connecting to the cluster, so old Hammer or Joule clients. It balances the things in a way that those old clients can understand. And it basically uses a score based on the number of PGs on an OSD, or the number of objects, or its space to use on an OSD. So it weights all those things together and then starts moving things for you. Because it's based on these crushed weights, it's still a bit imperfect. So then upmap is like the preferred solution, but upmap requires that all of your clients are Luminous. So here's the basic recipe for doing this. So for example, if you're using Crush Compact, then you would say Ceph balancer mode Crush Compact and Ceph balancer on, and then things should just happen. You should see backfilling happen, and that if you run Ceph OSD utilization, you'll see that things are getting a little squeezed a bit more tightly. In our case, though, it failed to do anything. And we had to increase some debug levels of the MGR, and then we found that it needed these two extra options. So these are, on a roller cluster, you would need to set these options, like, which are just shown there, and then you can reset it, and then it would work. Okay. So this is something that I haven't enabled everywhere yet, but it seems like the general framework is good, and over the next few point releases of Luminous, I expect this thing to really be tweaked to be working really well. We still have this question of how to replace many OSDs. So this is an old picture that showed in the Joule days using our scripts how we replaced 3 petabytes of servers with 6 petabytes of new hardware over several weeks. So like this plot on the left shows adding capacity to the cluster and then draining out some old servers, and adding another rack and draining out and adding and draining. And then the plot on the right shows the space used on individual disks. Some disks, the space going down, and then the new disks, the space used going up. It's not obvious how to do this with Luminous and the balancer yet. We did try. So the idea, I think, is that you should just, in the past, if you just added a whole rack of servers, this would be really disruptive to your clients. But I think with Luminous, the idea is that it should be okay, because the IOs are prioritized, and it's, the goal is that that's how it is. So we tried it with adding one server to our S3 cluster, and it was basically transparent latency-wise, so the clients didn't notice. But it did take 5 days to backfill one server, so this is probably a long time. And then there was some issue, I think that there's some bug related to the way it's deciding which objects to move and in which order. Because during this intervention, we had 5 million objects that undegraded, which is unusual. There's also, by the way, just like, if you notice, ever in your Ceph cluster, PG is going into activating plus remapped. Okay, this is like a hot issue at the moment. Click this tracker link and then follow the instructions. Okay, there's one of the new mechanism in Luminous to protect your OSDs from getting too much data, and that can go wrong in a couple of cases. Now I have a little bit of feedback about the ceph-volume tool, which is in Luminous, it's the preferred way to prepare OSDs. So it's like tooling for preparing your disk. This is how things look in Joule. Okay, if you're an admin and you log into a server and you want to see what's on my system, what are the disks here and how are they used? Well, you got a list of all of your devices. The SDC is a journal device. The SUD is an OSD, and it tells you it's like everything's very obvious. And by the way, there's tooling already existing for replacing failed disks or preparing them with flash journals and things like this. This is how things look in Luminous. Okay, this is like the new improved tool, right? So, Ceph is moving towards the usability direction, but I think this is a bit of a step back. But admittedly, it is still a work in progress. From here, it's really, this is designed for an LVM expert, not me. Also, you can't tell from the output which disk is the broken one. You can't tell. There's no dev STA, there's no slot number or something. You have to. These are all sim links. All these like block things are sim links that you have to follow through to find where it is. And then using Flash, there's no simple tool to just say I want this OSD to use spinning disk and Flash. Just do it in one line. This doesn't exist yet. So I hope that gets better. Now, just very quickly, plugging some of our friends. So, we're in this high-energy physics community, and if anyone else here is in this academic area, we meet monthly to share our experiences with similar use cases. So there's a couple of links there to get more info. And just plugging one of our closest friends in South Africa, they're building something called the Square Kilometer Array, which is a huge radio telescope, and they're using Ceph. The South Africans are using Ceph for a smaller version of the Square Kilometer Array. So they have a 5 petabyte cluster at the moment that they're going to expand to 20 petabytes, and yeah, they're happy Ceph customers. So. And there's some contact information if you want to do more from those guys. That's it. Any questions?
How are you handling the scrubbing stuff? So you scrub and normal scrub? Any special measures?
Yeah. So I think the only so we tune we have a scrub sleep. I think it's 50 milliseconds or something. I think it's around 50 milliseconds. And long time ago, we tuned the scrub stripe width option, I think, to make that. I mean, we just tested. We basically just did a parameter sweep to see what's the. We look at the latency, and then we enable a lot of scrubs, and then we just see what's transparent. So yeah, we tuned that long ago, which was probably in the hammer days, and we just haven't updated the configuration since then, so it seems to be okay.
And what does the scrub sleep does?
Scrub sleep injects like a pause between. So the way that Ceph scrubbing works is it grabs say, I think it's 25 objects, and then it starts reading them and comparing with the replicas or the ratio coding shards. And sleep injects a sleep in between each of those to let something else do some work, basically.
Okay, thank you.
I mean, just to say that things have vastly improved from the way that they were in the hammer days. Okay, in hammer scrub was a major problem. Now it's not really a problem in my experience.
So you said that you use the Manila driver and it would work for multi-tenancy, but basically all the virtual machines need to be connected to the Ceph cluster itself, right? Isn't this security-wise a problem?
So yeah, you should look at how Manila does it. It's really clever. I think John wrote it. Yeah. Right? The Manila shares. The mechanism is really cool. Basically, okay, so what do you want? You want each client to get a different CephX key, right? But you don't want to create a pool for every user, right? That would suck. So that's why Rados now has this thing called namespaces. So within one pool, you can have multi-tenancy in a pool, okay? So that solves the fact that you have several users using one pool. They all write their objects to a different namespace in that pool, which is actually just an object prefix. Then you don't want nasty users to connect to the MDS and do weird metadata hacking around anywhere in the namespace, right? So the MDS has a capability, you can basically secure one CephX key to a prefix in the file in the CephFS namespace. So basically in the end, the user clicks to the website, creates a share, that gives them a key that can mount the CephFS at a prefix in a namespace in the Rados pool. So this isolates them completely. It means it's creating them their own personal filer. It's not a shared file system to be accessed by anyone and then authenticated by Kerberos or something like that. That's not what it is. It's a unique empty NFS-like service for each user.
Do you have any experience on using Samba on CephFS?
No, not too much. No. Yeah. Do you? I would love to see if it's working or not.
No, I have someone who has.
Okay.
Thank you.